AC motors. Objectives are to discuss the operation of an induction motor, identify and explain the operation of various three-phase motors, explain how a split-phase condition is created, discuss the purpose of an AC motor protection circuits, list the common causes of motor failure, and explain the basic troubleshooting techniques for AC motors. Some of the keywords and terms used are branch circuit protection, dedicated line, locked rotor condition, rotor, run protection, running windings, Selson unit, service factor, shading coil, shading dipole, single phasing condition, slip, splitting phases, squirrel cage, starting windings, stator, synchro, and synchronous speed. (13.1) Induction motors. The induction motor is a special class of motor. Its name implies the motor operates on the theory of induction. In Chapter 12, the terms mutual induction and self-induction were introduced. Both of these terms apply to the induction motor in a slightly different manner. A motor converts electrical energy into mechanical energy. The mechanical energy takes the form of a rotating shaft. The rotation of the magnetic field inside of the stator produces power in the same way as the revolving field stationary armature from the three-phase generator. The stator of a three-phase induction motor is a mirror image of the three-phase alternator. See figure 13-1. The stator consists of stationary windings in a circular pattern inside a housing. When the three-phase power is applied to the stator, the coils in the stator produce electromagnetic fields in the same pattern produced by the revolving field in the alternator. Since the field rotates inside the alternator, the pattern of magnetic field poles inside the motor stator also produces a rotating pattern. The rotor revolves inside of the stator housing. The stator induces an EMF on the rotor. This action is much like the operation of a transformer. Figure 2 shows this. Think of the rotor as the secondary of a transformer and the stator as the primary. The rotor is constructed of soft iron laminations with copper or aluminum bars running through the outside edges. These bars act like the secondary windings. The stator induces an EMF on the rotor bars, causing a current to flow through the bars. The bars connect at the ends of the rotor. Again, the bars connect at the ends of the rotor, completing the circuits and producing a magnetic field between the rotor bar pattern. The magnetic field on the rotor follows the rotating magnetic field in the stator. As the rotor turns, the rotor bars cut across the magnetic field produced by the stator. This action adds to the currents in the rotor bars. Note the similarities to the generator and transformer action. The term squirrel cage is used to describe the type of rotor in the common three-phase induction motor. If the rotor were made up of soft iron laminations only, it would simply vibrate when the stator was energized. To produce the rotation, either a squirrel cage or other specially constructed rotor must be used. The other special rotors will be discussed later. In figure 13-3, a detailed illustration of a typical three-phase motor. The stator is inside the heavy cast iron frame and consists of coils made from moisture-resistant magnetic wire. The rotor bars are inside of the soft iron laminations of the rotor. This type of rotor construction enhances the strength of the magnetic field of the rotor. The rotor is mounted on a steel shaft with bearings. The bearings support the rotor as it turns inside of the stator housing. The rotation of a three-phase motor is reversed by reversing the connections of any two leads. Reversing any pair of motor leads or reversing any pair of motor lead connections causes the field of rotation inside the stator to reverse. Synchronous speed. Synchronous speed is used to describe the speed of the stator's rotating magnetic field. The rotating magnetic field speed is the product of the frequency of the three-phase electrical supply and the number of poles inside the stator housing. Because of this, the synchronous speed can be calculated using the following formula shown on the screen. Inserting the frequency coming from a standard outlet (60 Hz) into the formula we just showed along two poles, one pair from a motor, the equation becomes the following, shown on the screen. The synchronous speed of a three-phase induction motor with one set of wire coils per phase is 3,600 RPM. If there are two sets of coils per phase, then the synchronous speed would be 1,800 RPM. As the number of coils or poles per phase increases, the RPM of the motor decreases. Slip. Remember, rotor current is dependent upon the stator. As the rotor turns inside of the stator housing, the rotor bars cut the magnetic field of the stator. The action of the rotor bars cutting the magnetic field produces a heavy current. If the rotor catches up to the synchronous speed of the magnetic field in the stator, the rotor bars would not cut across the magnetic field. Consequently, in most motors, the rotor travels slower than the synchronous speed of the stator. The difference in these two speeds is described as slip. Generally, slip equals to 5% of the motor's RPM. A 4-pole motor with a synchronous speed of 1,800 RPM would have an actual speed of about 1,725 RPM due to the slip. The exact RPM of the rotor is dependent on the number and size of the rotor bars embedded in the rotor. When the motor is loaded with a heavy mechanical load, the rotor slows down and the percentage of slip increases. Again, when the motor is loaded with a heavy mechanical load, the rotor slows down and the percentage of slip increases. As the slip increases, a greater current circulates in the rotor circuit, which then produces a greater torque. Types of induction motors. Induction motors are used in a wide variety of situations. These motors are subject to different power sources as well as different loads. To supply these varied needs, induction motors have been created with a number of interesting features. Some important induction motors are the three-phase synchronous motor, the wound rotor motor, the dual voltage motor, the single-phase induction motor, and the capacitor start, capacitor run motor. Also, the repulsion induction motor, the shaded pole motor, and the stepping motor are some of the types of induction motors discussed. First, the three-phase synchronous motor. The three-phase synchronous motor derives its name from the fact that it rotates at the same speed as the rotating magnetic field. This action is accomplished by using a squirrel cage rotor and embedding a set of windings inside of the rotor. The rotor windings are constructed much like an electromagnet. The motor starts at the same as any induction motor and reaches near synchronous speed. To create a synchronous state with the stator, the windings on the rotor are energized by a DC source, and the rotor becomes an electromagnet. The rotor develops its own north and south pole, and that is independent of the induction of the rotating magnetic field in the stator. There is no slip to maintain, thus the rotor travels at the exact same speed of the rotating magnetic field. This motor is used in applications where a constant speed must be maintained under a changing mechanical load condition. The wound rotor motor. The wound rotor motor uses a stator constructed like a regular three-phase induction motor. However, its rotor is made of three sets of windings wrapped around soft iron laminations. The three sets of windings in the rotor are connected to slip rings and brushes. The rotor circuit is connected to a rheostat. The windings are similar to the squirrel cage rotor. The motor is started and then brought up to near synchronous speed. The speed of the motor can be varied by adjusting the rheostat. In the control circuit outside of the motor housing, this allows the current induced in the rotor windings to be varied. By varying the currents through the rotor circuit, the speed of the rotor can be adjusted. Although a full range of speeds cannot be accomplished this way, a great deal of variation in speed can be achieved. The dual voltage motor. The typical stator housing coils can be connected for more than one voltage. A dual voltage motor is a motor that has the stator coils arranged in pairs. The pairs of coils can be connected in series or in parallel, allowing the motor to be used with two different voltages. Three-phase motors are commonly dual voltage motors. A typical three-phase motor is rated for 240 or 480 volts. This means that the motor can be operated by either 240 volt or 480 volt power supply. A dual voltage motor is economical because fewer motors have to be stocked. The typical connection diagram of a dual voltage motor is shown in figure 13-4, shown on your screen. Induction motor. Single-phase induction motors are used in many home appliances. Three-phase electricity is not readily available. Most single-phase motors can be run in either clockwise or counterclockwise direction. To reverse the direction of rotor rotation, you must reverse the connections to the start windings. Not all single-phase motors are designed for reversing rotation. In industry, three-phase electricity is used to run large induction motors. Other means must be provided for starting single-phase induction motors. If, for instance, a single-phase current could be divided into a polyphase current, the starting problem would be solved. This action is possible, and it is called splitting phases. Two methods are used to produce a split phase. One method uses a capacitor, and the other method is based on induction and inductive reactance. See Figure 13-5. Inductive reactance will be studied in the next chapter, and capacitance is discussed in chapter 15, so only the basics are covered here. Inductive reactance, phase splitting. When wire is shaped into coils, the coil creates a certain amount of inductive reactance. Inductive reactance means that there is a force that opposes the current flowing through the coil. The amount of opposing force depends on the number of turns of wire in the coil. More turns of wire produce more inductive relative force. The induction causes the current flowing in the coil to slightly lag the applied voltage. Two coils having different numbers of turns of wire will have different amounts of inductance. Since the current from these coils occurs at two slightly different times, the magnetism in the coils also occurs at two different times. This action is the basis for splitting phases. If the single-phase current flows through two parallel paths that contain unequal amounts of inductance, one current lags behind the other. The phase displacement will exist between them, and a two-phase current has been created from a single-phase current. The many turns of wire that comprise the field windings of the induction motor are excellent inductors. They can be used for the purpose of phase splitting. A schematic diagram of a split phase motor is shown in Figure 13-6. The starting windings consists of many turns of relatively fine wire. The running windings have many turns of heavier wire. The windings are placed in slots around the inside of the stator. When electricity is applied to the motor terminals, current flows in both windings because they are in parallel. The running winding has many turns of wire and a high inductance. This causes the current to lag almost 90 degrees. The started windings of fine wire have much less inductance. The current does not lag by as great an angle. The phase displacement creates a rotating field similar to the three-phase motor, and the rotor starts to run. When the motor reaches speed, a centrifugal switch opens the starter winding circuit. The motor then runs as a single-phase inductor motor. The fine wire in the starting winding cannot withstand constant use, so it is cut out of the circuit after it has performed its function. Capacitor phase splitting. The second method of phase splitting involves the use of a capacitor. If a capacitor is connected in series with the starting winding, a much larger phase displacement can be created. A larger phase displacement means that the motor will have a much higher starting torque than an induction start motor. The capacitor is switched out of the circuit when the motor approaches full speed. See Figure 13-7. This motor is called a capacitor start induction motor. These motors are used for many jobs around the laboratory and home. They maintain a fairly constant speed under varying loads. They do not overdevelop or they do not develop a strong starting torque as compared to the three-phase squirrel cage motor. A capacitor start motor is shown in figure 13-8. Note the starting capacitor mounted on top. The capacitor start capacitor run motor. The capacitor start capacitor run motor is designed for heavy mechanical load conditions when only single-phase power is available. It is similar to the capacitor start motor, but this motor uses the same size wire on the starting winding and the running winding. The two capacitors are connected to the motor windings, one capacitor to start the motor or to start winding, and the other to the run winding. Again, one capacitor is connected to the start winding and the other to the run winding. For these, see figure 13-9. Both capacitors are energized while starting the motor. The starting capacitor is disconnected by the centrifugal switch when the running RPM is reached. The other capacitor is left continuously connected to the run winding. This motor is designed for high starting and good running torque under changing mechanical load conditions. Single-phase air conditioning equipment is a major application for this type of motor. A repulsion induction motor. A repulsion induction motor resembles a DC motor because it also has a commutator and brushes. However, in the repulsion induction motor, the brushes are connected to each other rather than to the source of power. The brushes are arranged so that only selected armature coils are closed to form complete circuits at any given time. The currents induced by transformer action in the rotor windings are displaced by the shorting brushes. Poles are created that oppose the stator poles. Rotation is started by repulsion. When the motor reaches about 75% of its speed, a centrifugal shorting ring shorts out all of the commutator sections. The motor runs as an induction motor. The repulsion motor has high starting torque, but it does not quickly come up to speed under load. It is currently being replaced by less costly capacitor start motors. Shaded pole motor. A two-pole motor having an uncommon method for starting rotation is the shaded pole motor, shown in figure 13-10. The rotor is a squirrel cage type. The stator resembles the common DC motor, except that a slot is cut in the face of each pole and a single turn of heavy wire is wound in the slot. This is called shading the pole. This single turn of wire is the shading coil. The action of the shading coil can be seen in figure 13-11. As the current rises in the first quarter cycle of the AC wave, a magnetic field is formed in the field winding. However, the expanding magnetic field cuts across the shading coil. This interaction induces a current and thus a magnetic field that opposes change in the magnetic field of the field coil. When the wave is increasing, This condition tends to decrease and weaken the total field on the side of the shading coil. At the top of the AC wave, very little current change occurs. The total magnetic field becomes equalized across the face of the pole. When the current starts to decrease in the next quarter cycle, the polarity of the induced current in the shading coil resists the decreasing current. So the pole has a strong magnetic field on the right side. Notice in figure 13-11 again. During this half cycle, that the magnetic field has moved from left to right. It is this movement of the field that causes the rotor to start rotation. The starting torque of this motor is very weak, therefore it has many uses in items such as small fans and electric clocks. Stepping motor. The stepping motor derives their name from the fact that they rotate in steps or small angles, one by one. Figure 13-12. Notice that the stepper rotor resembles a gear. It has teeth around its entire circumference, and it is usually magnetic. The stator consists of a gear-like structure with windings embedded in a pattern of two-phase, three-phase, or four-phase. The windings receive pulses of power rather than continuous application of power. The number of pulses applied to the stator windings determines the distance of travel the rotor makes. The rotor is a permanent magnet with a gear-like construction, but the number of teeth does not match that of the stator. When one of the stator windings receives an electrical pulse, the rotor only turns its teeth far enough to line up with the energized teeth in the stator. The speed of the rotor is determined by how fast the power is pulsed. The direction of rotation is controlled by the polarity of the electrical pulse of the stator. Once a certain position is reached, the magnetic pull of the rotor to the stator holds the rotor in position. Stepping motors are used for positioning mechanical levers and linkages. They are found in robots or disk drive systems. See figure 13-13. There are many varieties of stepping motor construction. However, their principles of operation are the same. The Celson unit, or synchro, that is sometimes called, is a unique transformer principle application designed to relay information through motor units. See figure 13-14. The Celson unit consists of two motor units. Each unit is constructed with a typical stator and windings spaced equally around the stator housing. Each rotor is similar to the synchronous rotor. The rotors are electromagnets. Both the stator units and the rotors are connected to each other. The rotors are energized by an AC power supply. When the rotors are energized, they induce an EMF on the stator windings. When energized, the two rotors will be at exactly the same angle of rotation. The unit is usually referred to as the transmitter, and the other is called the receiver. When the transmitter is rotated by a mechanical force, the receiver duplicates the exact same turn. These units are used on ships to indicate rudder position. They can be used to monitor change in position of almost any mechanical item such as a weather vane or a gun turret. Now review questions for section 13.1. Refer to your text. Number 1. The stationary field poles and windings in an induction motor are called a what? Answer is a stator. Number 2. The rotating member of a three-phase induction motor is called a blank. It is a rotor. Number 3. What is the synchronous speed of a motor if it has 6 poles and is operating at 50 Hertz? For that, we use the formula shown on the screen, top right, where the synchronous speed equals to Hertz times 60 seconds in this case, all divided by the number of poles. And in this case, we have 50 Hertz times 60 seconds divided by 6, which ultimately gives us 500. And 500 is the synchronous speed of that motor. Question 4, define slip. Slip is the lag from synchronous speed of the rotor from true rotational speed of the stator field. Again, that the definition of slip is the lag from the synchronous speed of the rotor from the true rotational speed of the stator field. Number 5, who or how are dual voltage motors different from a regular induction motor? And the difference is that stator coils are wired in pairs and can be connected in series or in parallel. Number 6, a split-phase induction motor has many turns of fine wire in the start windings, and run windings are made with many or fewer turns of heavier wire. Number 7, how does a repulsion induction motor differ from a standard AC motor? The difference is that it has commutators and brushes connected to each other. Explain how a Celsin unit operates. And that is, in two identical motors, the rotor only is energized by AC. The rotor in the transmitter is designed to be moved to a certain position. The receiver rotor will match the same position by inducing a magnetic field on the stator winding. (13.2) Motor protection, failure, and troubleshooting. Motor protection is important to any motor system. Most motor protection involves safety devices installed in power lines that feed the motor. These devices protect more than just the motor. They protect the load and any other device connected in the motor system. Motor installation and protection. Unless the motor being used is very small, motors are installed with dedicated lines. A dedicated line means that the circuit is used for only one purpose. For a proper installation of a motor, two forms of protection are needed. In this delineated line, or in this dedicated line, branch circuit protection and running protection. Again, For a proper installation of a motor, two forms of protection are needed in this dedicated line, which are branch circuit protection and running protection. See figure 13-15. Branch circuit protection means that a fuse or breaker is installed to protect the circuit feeding the motor. This fuse or breaker can be set to trip if the current exceeds anywhere from 150% to 500% of the motor's full load current. The full load current of a motor is the current the motor is expected to draw while it is under full mechanical load. A table saw, for example, can be rated at 12 amps for full load condition. This means that when the saw is cutting the maximum size of wood it is designed for, it will draw 12 amps of current at the recommended applied voltage. When the saw is turning but not cutting wood, the amperage will be small in comparison, maybe as little as 1.5 amps. However, the circuit protection must be selected at a high enough level to allow for a high starting current or a surge. A brief surge as high as 600% of full load current can be obtained when the motor is energized. If the current or if the circuit protection is set too low, the fuse will blow or the breaker will trip. The second form of protection is called run protection. Run protection protects the motor from the excessive heat damage or fire while it is in a normal mode or operation. Run protection is a necessity since only a slight mechanical overload to a motor will, over a period of time, cause damage or fire. Running protection must be closely sized to a motor's service factor. All motors have a service factor. A service factor of a motor is its ability to withstand or avoid damage from an overload condition. The service factor is based on a percentage of a motor's normal current under full load condition. To interpret a service factor, subtract 1. Again, to interpret a service factor, subtract 1 from the number and multiply the remainder by 100. This gives you the percent overload a motor can handle. For example, if a motor has a service factor of 1.25, it can safely withstand a 25% overload. A motor with a 1.15 service factor can withstand 15% overload. A motor with a 1.0 service factor can withstand no overload. Motor failure. Most AC motors are of simple design unless brushes are used. They require very little maintenance. However, motors will eventually fail, and there are a few faults that account for most failure. Excessive bearing wear. The most common cause of motor failure is excessive bearing wear. Some bearings are sealed and do not require maintenance, while others require periodic lubrication. Dry motor bearings cause friction, heat up, and wear down rapidly. In a motor, there is very little clearance between the stator and the rotor. As the bearings wear down, the rotor will begin dragging on the stator. Usually this causes a loud roar or high, shrill, winding sound as well as excessive vibration. The worn bearings cause excessive load on the motor and cause it to go into an overload condition. Mechanical overload. Another cause of motor failure, small AC motors, is mechanical overload. An example of mechanical overload is when a power tool is used continuously under severe mechanical conditions. The tool heats up until the temperature exceeds the temperature rating of the stator's insulation. Once this occurs, the windings are irreversibly damaged. The damage can be so severe as to produce a short between the windings or to the iron laminations. Single phasing condition. Three-phase motors are often exposed to another damaging situation called single phasing condition. A single phasing condition occurs when the power supply to the three-phase motor loses one of its three lines due to an open or blown fuse. If the motor is running at the time the loss occurs, it will continue to run. However, there will be an increase in current in the two remaining motor windings. Unless the overload protection trips the relay coil in the starter, this current increase will damage the motor. Small motors can have a thermal device inserted in the motor windings that will open when excess heating occurs. This device offers protection for a motor experiencing mechanical overload or a single phasing condition. If this type of running protection is included as a part of the motor, the data plate will indicate that the motor is thermal protected. Locked rotor condition. The most severe damage occurs to a motor when it has a locked rotor condition. A locked rotor condition is when the motor is energized, but the rotor is not turning. A mechanical failure in the system to which the motor is connected can cause this condition. When locked rotor occurs, the current in the windings is extremely excessive and can severely damage the motor windings. Low voltage. Another common cause of excessive motor current is low voltage. Under a low voltage condition, a motor will maintain its horsepower output rating until the low voltage becomes so severe that the rotor locks. This low voltage condition causes excessive current in the windings while the motor is under mechanical load. Remember when checking for low voltage conditions, the motor must be under mechanical load, otherwise the voltmeter readings will not be accurate. Review the voltage drop formula for conductors in Chapter 3. As current increases, so does the voltage drop on a conductor. As mechanical load on a motor increases, so does the current. As the current increases, so does the voltage drop at the motor. Look at illustrations in Figure 13-16. Many burnt wirings or many burnt winding patterns can reveal why a motor failed. Troubleshooting motors. The most useful tool when troubleshooting a motor is the clamp Ohm meter. The clamp Ohm meter or the clamp ammeter operates using the transformer principle of induction. The ammeter clamps around the line to read such as in figure 13-17. The clamp is the primary coil and the secondary coil is inside of the meter housing. The current in the line being measured produces a flux field that cuts across the clamp. This generates an EMF that is measured by the meter movement. The clamp Ohm meter is used only for AC circuits. Its greatest advantage over the other forms of AC meters or AC ammeters is that the circuit does not have to be opened to connect the meter in series with the circuit. As you have learned so far, a properly operating motor should have a current reading higher than the motor's rating. A simple ammeter reading can tell you that, or a simple ammeter reading can tell you a lot about the condition of the motor. As the motor's windings break down, they will draw more current in the lines to the motor. This will show up on the ammeter. Another quick check is to measure and compare all three lines of the three-phase motor. The three lines should be identical current values. Any deviation from a near perfect match means the motor windings are breaking down. Bearing wear in motors can be identified by sound, vibration, or excessive heat at the bearing housing. Large industrial motors have the temperature monitors made from thermocouples to monitor bearing heat and windings. These monitors provide an accurate prediction of motor failure and allow the technicians to safely shut down the system and replace bearings or windings before failure occurs. Another useful tool is the Ohm Meter. As the name indicates, the Ohm Meter is a type of ohm meter that measures resistance in the millions of ohms range. This meter generally uses a much higher operational voltage than a standard ohm meter. A standard ohm meter uses 9 volts in the ohm meter circuit. A standard type of meter would not have sufficient voltage to detect a short or ground in a motor that operates at a higher voltage, such as 480 volts. And now review questions for section 13.2. What function does a dedicated line serve? It provides power for a three-phase motor permanently. What is the difference between branch circuit protection and run protection? Branch circuit protection is designed to protect the line that feeds the motor and plus the starting current so that it can be rated up to 500% of motor's full load current. The run protection is more sensitive to protect motor from overload conditions as little as 1.5 or 1.25% of full load. Sometimes it could be 1.15 or even 1.0 or no overload protection. Number 3, a motor with a service factor of 1.9 can withstand A or N% overload. And the answer for this fill in the blank is 9%, since 1.9, the answer for that is 90%. Number 3 is 90%, since 1.9 is basically 1.90 or 90. Multiply that by 100. Take out the 1, which is basically 1 for 1, or the service factor of 1 of the motor. Separate the 0.9, which is basically 0.90, and that will give you, when multiplied by 190%. Question 4. List 4 reasons for motor failure. 1 is excessive bearing wear. 2 is mechanical overload. 3 is single phasing, or the loss of a phase. And 4 is a locked rotor or low voltage condition. Question 5. The current values of the 3 phases of a 3-phase motor should be, fill in the blank, and they should be identical. There should be no voltage difference between any of the phases, or very little if any, and that is because there shouldn't be a voltage drop or a potential difference between the phases. Question 6. What is a Ohm meter? It is an ohm meter capable of detecting small shorts or grounds, again, that uses a much higher voltage than your common ohm meter. Chapter 13 Summary. Number 1, an induction motor changes electrical energy to mechanical energy. Number 2, in an induction motor, the field poles and windings remain stationary. Number 3, synchronous speed is used to describe the speed of a stator's rotating magnetic field. It can be calculated from the following formula. Synchronous speed in revolutions per minute equals to the number of hertz times 60 seconds divided by the number of pairs of poles. Number 4, in most motors, the rotor travels slower than the synchronous speed of the stator. The difference in these two speeds is slip. Number 5, there are a number of different types of induction motors. They include a three-phase synchronous motor, wound rotor motor, dual voltage motor, single-phase induction motor, capacitor start, capacitor run motor, repulsion induction motor, shaded pole motor, and stepping motor. 6. Single-phase motors split the incoming single-phase current into a polyphase current. 7. Split-phase induction motors have starting and running windings. 8. A dedicated line for a motor will often have branch circuit protection and running protection. 9. The common causes of motor failure are bearing wear, mechanical overload, single phasing condition, locked rotor condition, and low supply voltage. 10. A single phasing condition for a three-phase motor means that power has been lost to one of the three lines feeding the motor. 11. The clamp Ohm meter or the clamp on ammeter operates using the transformer principle of induction. Now for the test your knowledge question for chapter 13, AC motors. Name the different types of three-phase motors. And the different types of three-phase motors are synchronous motor, dual voltage motor, the single-phase induction motor, and the capacitor start motor. Or the capacitor start single-phase motor. Question 2. What electrical part do the motors in question 1 have in common? And the answer number 2 is that the motors all have a stator and they all have a rotor, regardless of the type. Again, the stator is the stationary windings in a circular pattern in the motor. The rotor revolves inside of the stator housing. Question 3. How do you reverse the direction of a rotation the direction of rotation for a three-phase motor? The answer is to reverse the conductors of any two of the three-phase lines. Again, reverse the conductors of any two of the three-phase lines. Question 4. How do you reverse the rotation of a single-phase motor? The answer is you reverse the hot and neutral connections. Question 5. Explain the operation of a three-phase induction motor. The answer is the stator windings, generally three pairs of coils, are energized with three-phase AC power, one phase to each pair. The AC or the AC lines or the AC connections are 120 degrees apart so that a rotating field is generated. Again, three-phase AC power, one phase to each pair. The alternating current is 120 degrees apart so that a rotating field is generated in the stator due to rising and collapsing magnetic field, or the AC current created by the AC current. A rotor is energized by the field using the transformer effect, or through the transformer effect, and is forced to follow the field. The slip or lag produces torque in the motor, as the slip produces, or is as the slip is a product of a higher magnetic force in the rotor coils. A mechanical force is produced by the rotor. Question 6. A or an blank, a heavy wire wound into a slot cut on the face of a pole. The answer is a running winding. Question 7. What is running protection? It is sensitive fusing or circuit breaker that protect from overload of motor lines. And finally, question 8. What is a service factor? It is the amount of overload that a motor could safely withstand, or the amount of overload protection or percentage that a motor could safely withstand. Again, usually given as a percentage. That brings us to the end of the chapter. Congratulations. You have earned this electronics course rank. Please continue your studies and remember to complete all reviews, quizzes, tests, and experiments related to this chapter. Thank you very much.